This is our Simul8 tutorial. This is a discrete simulator, and this introduction will teach you how to run some basic simulations. So let's start by opening up Simul8. Okay, so first thing I usually like to do is I right click on the clock, and I like to make it a digital clock. You don't have to, but I like to do that. Okay, and let's start very basic. So we have a start point. Now let's drag a cue. They automatically connect because these arrows are here. And activity. And an ending. Okay, our start point is what generates people. It generates customers entering your system. So how are the customers entering? The inter-arrival time is exponential. You have a choice. It could be normal distribution, gamma distribution, all sorts of distributions. But usually people stick with exponential when you don't have better information. And the average time between arrivals, this is not a rate, it's the average time between arrivals. Let's suppose this will be 4 minutes. So we put a 4 there. How do we know it's 4 minutes? If we click back on the clock properties, you see that the units for the simulation is in minutes. Okay. Another thing I like to do, go to File, on Preferences, and Distance. Set the travel time to 0. What this does is it doesn't actually compute the time it would take to travel from, let's say, here to here. In real life, it may very well take time, and you might want to code that in. But for our purposes, just so that we all get the same answers, let's set the travel time to 0, so customer will instantly go from here to here and from here to here when they're ready. Okay, let's go to the activity. So the activity, this is the server or the process. This is what has to get done. And let's say the server is also exponential. And let's say it's slightly faster than the incoming rate of customers. So let's say it's 3.8. So the average time it takes to service one customer is 3.8 minutes. Okay, as compared to the average time between arriving customers, that's 4 minutes. So think of it like every 4 minutes a customer arrives, and it'll take 3.8 minutes to eject the customer from the system. And when they get to here, the customer's gone. Think of this as a barber shop. Customers enter the store, they wait in line, or they wait in the waiting room, they get their haircut, and then they leave. All right, let's save it. So let's save it anywhere you want. Maybe this desktop, and let's call it single server 01. Okay. All right, let's run it for a week. Let's run it a little slowly, just so we could see it running. And you can see the customers arriving. See the clock? The clock changes every time an event occurs. A little slower. So a little bit slower. So the dot represents a customer, and we can see as long as the activity is busy, the customers will have to wait. They will have to wait in line. This is the waiting line. This is the queue. All right, let's speed this up a bit. So let me pause it. And let's speed it up to the maximum speed. And let's finish it. All right, so it just ran for an entire week. And that's 8 hours a day, 5 days a week. So 5 days. And it just continues from day to day. So this queue does not empty out at the end of each day, though you can program it to do that. Okay, so let's take a look at some of the statistics here. If you just hover over the queue, you see the average wait time was 23.74 minutes. Max wait, one person had to wait 91 minutes for his haircut. If we click on the queue and we look at the results, we can see that the average number of people in the queue at any given time is 5.54. And maximum, there was 22 people waiting for a haircut at one point. But the average, so this would be L sub Q, the average number of the average length of the queue, 5.54. And we already saw the queuing time. This would be W sub Q, the average wait time, 23.74. If we look at the activity here, its utilization was 88%. That means it was active 88% of the time. 12% of the time it was starved, which means it wasn't working. If this was a barber shop, 88% of the day he was cutting haircuts, and 12% of the day he was just doing nothing. Average end to end, 27.54 minutes. This is W. W is the average time spent in the system. And the average, if we want to see some more statistics here, the maximum time spent in the system was 96 minutes. All right, during this time, 565 people entered the system, and when time finished, one person was in the barber chair in the server, 13 people were waiting, and 551 people left. All right. Now, if we really want to get better data, let's run it for a year. So let's reset and run. So a year just went by, and as you can see, we're left with 16 people. That's not terrible, but to see what the average wait was, average wait was 78 minutes. That's not so good. So what can we do to speed things up a bit? Well, you can't really change the incoming distribution of customers. You can hire maybe another person to help speed up. So we can hire a second barber, or maybe we could speed up this barber somehow. Perhaps we can update some of his tools or his methods. Let's say we're able to speed him up a little bit, and we can get him to the point where it takes 3.5 minutes on average for a single haircut. So let's try 3.5 there. All right, let's run it for a year. And let's see what our average time spent in the queue, down to 24.5 minutes. So that's about 1/3 of what it was before. The tiny little change from 3.8 to 3.5 gave us a dramatic reduction in the waiting time. Let's say it was 3.9. So that's a little worse. Let's say the barber's slower again. Average wait time, 165 minutes. So you can see it's highly nonlinear. If the average inter-arrival time is 4 minutes, average time between arrivals, and the average service time is 3.9 minutes, we're going to have very, very big lines. $165 minutes. One person waited 756 minutes. Of course, in real life, he would probably leave. No barber is that good that he would wait 756 minutes for a haircut. So let's hire another barber. So if we right click on this activity, let's go to the duplication wizard. One copy to create. New location. These are the coordinates, X, Y coordinates. And there we have it. It's all linked up already. And this one is identical. So activity 2, also 3.9. All right, so let's see what happens. Let's reset it and run. Okay. What's the queuing time now? 1.18 minutes. So by hiring another barber, we've dramatically reduced the waiting time down to 1 minute. So you can't really use your common sense here. You have to do simulations and use formulas. It's hard to figure out what will happen with your basic intuition. Okay. Now, let's look at a famous problem where we have the same number of resources but used in two different ways. And we'll see that we'll get a dramatic difference in the queuing times. So let's start over. I'm just going to delete everything. All right. I have a start point, and then what I'm going to have is a queue. I unclick the arrows. See, the arrows are gone. So now when I drag it, nothing connects. I'll connect the things next. All right, so each of these queues will be linked to an activity. Oops. And we need an endpoint. Now let's connect. So to connect, you click on the component, see the four triangles, the arrows, just drag from there. Just click on any one of these arrows and it will connect. Now let's connect these queues to their activities. Okay. And let's connect the start point to the queue. All right. Now, customers are going to be entering from the start point. So let's route out a uniform output from the start point. In other words, when a customer enters here, customer will be equally likely to enter one of these three queues. It doesn't matter how long the queues are. It's just going to be a 1/3 probability, 1/3 probability, 1/3 probability. All right, let's come up with some data. So let's say exponential random variable. And suppose that the average time it takes to handle a customer is 10 minutes. All right, so let's change these to exponentials. and exponentials. Okay, so average time to handle a customer is 10 minutes. That's 6 people per hour for each one of these. And suppose that the average time between arrivals, well, let's look at the rates. So mu would be 6 customers per hour. So our servers can actually handle 18 customers per hour. So as long as fewer than 18 enter per hour, our system will not blow up. Our queuing system will not blow up. So let's say the average time between arrivals is 4 minutes. That would be 15 customers an hour enter. And we have enough server capacity to handle 15 customers per hour. All right, let's run it for a day. Let's run it slowly, just to see if it's working. Okay, it seems to be working. I'll pause it. And let's run it for 1 year. Speed it up. All right, so what happened here? Let's look and see how long did the average person spend in the system. 58 minutes approximately. Average waiting time for this queue, 46 minutes, 51 minutes, 45 minutes, okay? And what's the average length of each queue? Average length, on average there are 3.88 people in the queue at any given time. Maximum was 30. All right, for that one, this one here, average four people on average, and this one 3.7. Looks like about 4. So imagine this is a store, and you have 3 lines. The customer randomly enters each line, and on average there'll be about 4 people per line. We're talking 12 people waiting at any given time on average. And the queuing time is about 45 minutes, it seems. 48 minutes perhaps. So they're waiting for quite a while to get service. Okay. Now let's see how we can use the same resources but in a different configuration. So let's start with a start point. And let's have 1 queue this time. And with this 1 queue, we'll have 3 activities. Or we'll just take the next available customer, like you usually do. All right, and we need an endpoint. All right, and let's get the data the same. So let's see, exponential 10. So exponential 10, exponential 10, and exponential 10. Okay. This is supposed to be exponential interarrival time 4. Let me save it in case it crashes. It does crash sometimes, so you might want to save it. All right. So I think we're ready. Let's reset. Let's run them both. All right, we just ran them both for a year. For this first system, average time spent in the system, so that would be W, average time spent in the system, 58 minutes. For the second system, 26 minutes. Let's look at the queuing times. 46 minutes, 51 minutes, 45 minutes. $16 minutes. So take a look at this. It's the same number of servers. Each one is working at the same maximal rate. Same input stream of customers. See, 31,000 customers arrived within the year. But by configuring your system this way, the average length of this line is only 4 people. And remember, we already saw before, this has 4 people, this has 4 people, and this is 4 people on average. So this, you would expect this line to be really long, right? What your intuition would say, these would be shorter, and this one would be maybe 3 times as long. But in fact, it's more like, 3 times as short. And when people get on this line, it's not at all a shorter line. 46 minutes is what they'll wait, but on this line, they're only going to wait 16 minutes. Okay, so let's just double check again. Make sure I'm not trying to pull a fast one. Exponential 10, exponential 10, exponential 10, exponential 10, exponential 10, exponential 10, exponential 4, and exponential 4. Now you can try this with other distributions. So we can change this to a a normal distribution, standard deviation 3. Normal distribution, say standard deviation 3. Normal distribution, standard deviation 3. Right. Let's change them all. All right, I think I got them all. Let's reset and see what happens now. Average time in the system, 35 minutes. Average time in the system, 17.9 minutes. So it's not as dramatic, but the bottom system is twice as good. At least for getting people out of the store faster. Okay, now we could also add what's called a resource. Let's say this is a special device that that the servers need. Let's say there's only 2 available. And let's go to the activity, and we'll say that this activity needs to use resource 1. So for each activity, let's say that we need to add a resource. And resource, add resource 1. Okay, so now think of this as 3 barbers and maybe 2 hair dryers. And let's do the same here. Let's have another resource. Let's say there are 2 available. And let's add a resource. These guys will use resource 2. Resource. Okay. So let's reset and then run. Not very good, right? Looks like this resource really slowed things down. As you can see, the system exploded, blew up. If you want to see what happened, let's run it slowly for a little bit. See, watch the resource go down. Now, I'm not sure why this one isn't running. Maybe you have to hover over it. Perhaps it's just going so slow. Speed it up a little bit. Here's a little faster now. You can see it better. So you see, an activity becomes starved when the resource is not available. All right, so let's see if we can fix things. That's the nice thing about a simulation, is you can fix things. Well, you can fix things by perhaps speeding up some of these activities. Let's say this one is going to be a lot faster. Let's say this one will be a lot faster. Let's see if that's enough to fix it. And it seems to do the trick. So we still have something not so great about this one. 1,000 minutes was the average wait. This one had an average wait of 20, and this one had 328. Well, we know this one was better. So let's route out so that we go to the shortest queue. This makes more sense in real life, right? If someone can, they're going to choose the shortest line. Okay, let's reset. All right, so the system seems to be running better this time. Notice over here we don't have to do that. It'll automatically go to the next available. All right, so we'll continue in the next episode, and in the next episode we'll see how to input our own distributions, our own probability distributions. So it looks like we got the results, so let's see. 29 minutes average wait, 42 minutes, 42 minutes. All right, not too bad. And this one is 37 minutes. Average time spent in the system, 45 minutes end to end. 45 minutes. All right, so as you can see, by giving the option to choose the shortest queue, it does make it a lot more competitive with this system. It's not that different.